Acid-base equilibrium. Review of the Arrhenius and Brønsted Lowry acid-base theories. In this tutorial, we will be going over the definition of a labile proton, Arrhenius acids and bases, Brønsted Lowry acids and bases, amphiprotic substances, and conjugate acid-base pairs. Arrhenius acid-base theory. Let's talk about the definition of a labile proton. This is the proton that an acid can lose or a base can gain in an acid-base reaction. Let's talk specifically about Arrhenius acids and bases. In this theory, an acid is a substance that yields hydrogen ions in water, forming an aqueous solution. An example of this is hydrogen chloride gas being bubbled into water, forming hydrogen ions and chloride ions. An Arrhenius base is a substance that yields hydroxide ions in water, forming an aqueous solution. An example of this is when we have solid sodium hydroxide dissociating into sodium ions and hydroxide ions. The presence of the hydroxide ions is what makes this a base. Limitation of this acid-base theory. This Arrhenius theory is restricted to an aqueous environment. Now let's talk about the Brønsted Lowry acid-base theory. In this theory, an acid is defined as a proton or hydrogen ion donor. An example of this could be something like nitric acid, HNO3. A base is defined as a proton or hydrogen ion acceptor. An example here could be something like ammonia. This theory is not restricted exclusively to an aqueous environment. What to know about Brønsted Lowry bases? Brønsted Lowry bases must have a non-bonding electron pair to bind a hydrogen ion. An example could be something like ammonia. Here is the structural formula for ammonia. Notice that it has a lone pair right here, which can be a hydrogen ion acceptor location. Water can also act as a Brønsted Lowry base. Because in the structural formula for water, there are two lone pairs, here and here, these are also possible spots where a hydrogen ion could form what we call a coordinate covalent bond or a dative bond, accepting a proton and therefore falling under the category of a Brønsted Lowry base. The last example here is the carbonate polyatomic ion, CO3-2. When we look at the carbonate ion, we can see multiple locations, especially down here with these oxygens, where a hydrogen ion could be accepted to form a coordinate covalent bond. So therefore, the carbonate ion is an excellent example of a Brønsted Lowry base. Amphiprotic substances. An amphiprotic substance is a substance that is capable of acting as either an acid or a base. An amphiprotic substance is going to act as a base when combined with something more strongly acidic than itself. It's going to act as an acid when combined with something more strongly basic than itself. Here's an example of an amphiprotic substance. We're starting out with hydrogen chloride gas being bubbled into water, and the focus here is looking at the water. As this reaction proceeds towards completion, we're going to form the hydronium ion, H3O plus 1, and the chloride ion, Cl-1. In this scenario, the water is going to act as a Brønsted Lowry base. So BLB is what we're going to use to represent Brønsted Lowry base because no one wants to write that out. The water molecule is going to accept the hydrogen ion from the HCl. And as a result, the hydronium ion, H3O plus 1, will form and be labeled as a conjugate acid, which we will review later on in this video. So in this particular scenario, water is a Brønsted Lowry base because it accepted a hydrogen ion. Let's look at our next example. We have ammonia, which we know is a weak base. Here, water is going to act as a Brønsted Lowry acid, as it's going to donate one of its hydrogens to the ammonia. As a result, we form the ammonium ion, which we know is a weak acid, and the hydroxide ion, which will be the conjugate base of the water. So again, in this particular scenario, water is donating a hydrogen ion to the ammonia. The ammonia accepts that hydrogen ion because it is a weak base, forming the ammonium ion, and the hydroxide ion is formed. So this is an example where water in one scenario is a Brønsted Lowry base, and in a different scenario is a Brønsted Lowry acid. Conjugate acid-base pairs. A conjugate acid-base pair is an acid and a base such as HX, where X is representing any anion, and X minus 1 that differ only in the presence or absence of a proton. A conjugate base is formed by removing a proton from an acid. A conjugate acid is formed by adding a proton to a base. Here's an example. So we have HF plus H2O yields the hydronium ion, H3O plus 1, and the fluoride ion. In this scenario, HF is a weak acid because it's going to donate this hydrogen ion to the water. Water is classified as a weak base because it accepts that hydrogen ion from the hydrogen fluoride. F minus 1 is the conjugate base of the HF because HF and F only differ by a hydrogen ion. The hydronium ion is classified as a conjugate acid of the water because, again, they only differ by one hydrogen ion. Identify the conjugate base of the following Brønsted Lowry acids. So each of these are an acid. What we're looking for is the conjugate base. So whatever we see in these blanks should only differ from the conjugate acid by one hydrogen. So HiO3, the conjugate base of that is IO3 minus 1 because we see a difference of one hydrogen ion. For NH4 plus 1, the conjugate base would be NH3. Again, we see a difference of only one hydrogen ion. For H2PO4 minus 1, the conjugate base would be HPO4 minus 2. So here we have two hydrogens, while over here we only have one hydrogen. Finally, HC7H5O2, the conjugate base of that is going to be C7H5O2 minus 1. Notice the hydrogen that is removed is the hydrogen at the beginning. This is an example of a labile proton. The other hydrogens here are attached to the carbon. Those are not being removed. Let's go on and identify the conjugate acid of the following Brønsted Lowry bases. So these are all bases. Again, they will only differ by one hydrogen. So in each one of these blanks, we should see an addition of a hydrogen to each one of these bases. So our first one is HSO3 minus 1. The conjugate acid is H2SO3. Notice that there's one hydrogen here and two hydrogens here. For F minus 1, the conjugate acid is HF. So we see again the difference between no hydrogens and one hydrogen. For PO4 minus 3, we're going to add one hydrogen. So this is HPO4 minus 2, and we see that the charge goes down by 1. And finally, CO, the conjugate acid of this, is HCO plus 1. For each of the following equations, identify the Brønsted Lowry acid and base on the left side of the equation. Then identify the conjugate acid and conjugate base on the right side of the equation. So what I'd like you to do is stop, see if you can do this on your own, and then check your work. Okay, welcome back. Let's see how you did. So when we look through this first example, we want to say to ourselves, okay, our Brønsted Lowry acids and bases are going to be over on the left-hand side. The conjugate acids and bases will be labeled over on the right-hand side. So when we look at this first one, we recognize that NH4 plus 1 is an acid because This has one more hydrogen compared to the NH3 over on the product side. If NH4 plus 1 is my acid, that means CN minus 1 must be my base. Now we're going to figure out the conjugate acid-base pairs. Again, we are looking for a difference here between these pairs of only one hydrogen. So if NH4 plus 1 is my acid, that means NH3 must be my conjugate base, because here we have 3 hydrogens and here we have 4 hydrogens. If NH3 is my conjugate base, that must mean that HCN is the conjugate acid. Again, here we have 1 hydrogen, and over here we have no hydrogens. That makes this a conjugate acid-base pair. Let's look at our next example. This one is a little bit harder to do, so when you see something that's complicated as this, focus on what you know. The hydroxide ion is always going to be a conjugate base. Always. As soon as you see OH minus 1, that's a conjugate base. So if this is a conjugate base, that means the CH3 NH plus 1 must be a conjugate acid. Once we know our conjugate acid and our conjugate base, we can figure out which one is the Brønsted Lowry acid and base based on conjugate acid-base pairs. So CH3N must be the base, and for the other reason is the fact that it has absolutely no hydrogens except for the ones bound to the carbon. So that's going to be our base. And here water is acting as an acid because, again, here we have 2 hydrogens and over here we only have 1 hydrogen. Let's look at our last example. Here we don't have anything as straightforward as having a hydroxide ion or a hydronium ion. So I would start with the PO4 minus 3 because it does not have any hydrogens at all. That means that has to be my base. And if PO4 minus 3 is my base, that means that HCHO2 must be my acid. Now I can figure out the conjugate acid-base pairs. So CHO2 minus 1 is my conjugate base because the acid and the base differ by 1 hydrogen. If CHO2 minus 1 is my conjugate base, that means that HPO4 minus 2 has to be my conjugate acid. Again, the base over here has no hydrogens, and over here, the conjugate acid has 1 hydrogen. Writing acid-base reactions. The hydrogen oxalate ion, HC2O4 minus 1, is amphiprotic. Write a balanced chemical equation showing how the hydrogen oxalate ion acts as an acid towards water. Then write a second balanced chemical equation showing how the hydrogen oxalate ion acts as a base towards water. So in our first equation, we're going to write the hydrogen oxalate ion, then water, and we can see how the hydrogen oxalate ion donates that hydrogen to the water. As a result, we form the hydronium ion and the oxalate ion. In the second equation, the hydrogen oxalate ion is going to act as a base. So we write our ion, then water, and as a result, we're going to form the hydroxide ion and oxalic acid. So in this case, water is donating one of its hydrogens to the hydrogen oxalate ion. As a result, we form the hydroxide ion and oxalic acid. So the difference between the hydrogen oxalate ion and oxalic acid is again 1 hydrogen. So what did you learn in this tutorial? We talked about the definition of a labile proton and saw some examples. We reviewed the Arrhenius acid-base theory. We also reviewed the Brønsted Lowry acid-base theory. We talked about amphiprotic substances and then reviewed conjugate acid-base pairs. Need more help? Feel free to contact me. Have a great day.